Hi, everyone. Welcome to Riot's Lunch and Learn series. My name is Caroline Griffin. I am Riot's Director of Operations. You have found the place where we feature all of Riot's partners. Today, courtesy of AEM Group and Penny Hoagland, we have Jason Lee with Eaton here with us to talk about power storage solutions for IoT and backhaul infrastructure. Now, I know you are all here to see Jason, so I'll just give you a couple quick reminders before we get kicked off. One, this meeting is being recorded. It'll be posted to Riot's YouTube channel and then shared out via the meetup group where you signed up for this event. Two, all of the questions may be asked via the chat box. I will be monitoring the chat box throughout the event, and then we'll make sure all of the questions are answered at the end of the event. And the third thing is the best way to view this presentation is in speaker mode. That'll give you a full view of Jason's presentation, and please do keep yourself muted throughout the presentation. Again, if you need to have any questions asked, please do those via the chat box. But without further ado, thank you so much for being here with us today, and I will hand it over to Jason.
Okay, thank you, Caroline. Welcome, everyone. I am Jason Lee. I'm a global product manager at Eaton in our electronics division, and I handle our supercapacitor product line. As Caroline mentioned, AEM is our local manufacturer's representative, and Penny Hoagland is online with us today as well from AEM. I'm excited to talk today about using supercapacitors to power IoT devices. Our history goes back in these applications, really starting about 20 years ago in gas and water meters. So we'll give some examples of that, and that'll be a large focus of today's presentation. I'll go through some main energy storage technologies, how they work, some of the key advantages, and look at, in a lot of cases, how combining these technologies to yield optimum results for your application. And then we'll go through some specific IoT power examples that we've done designs with different customers, and then just wrap up with a brief overview of our product line. So looking at the technologies, so we'll talk about supercapacitors, hybrid capacitors, or apologize for the spelling there, hybrid supercapacitors versus batteries. And so one thing we look at in comparing technologies is called a Ragone-Plot. And it plots here on the y-axis energy density and on the x-axis power density. So items or technologies in the bottom right have higher power but low energy. You can also think of this graph on a time scale if you divide the energy by the power. And so things that are in the bottom right, again, can provide high power, but for a short amount of time. In contrast, batteries kind of clustered in the middle there, but as you go further up and to the left, higher energy for sure, but lower power. This means they're good to store a lot of energy, but not good at releasing it quickly. This would get us from a time scale into the several minutes to hours of discharge time. And certainly as you work up to fuel cells, you're definitely into the hours of discharge times. Okay, so looking at some of the more details on these different technologies, I won't cover fuel cells here. We'll mostly focus again on batteries and the different types of supercapacitors. Starting with traditional supercapacitors, you might hear them called also ultracapacitors or EDLCs. They really mean all the same thing. There are two electrodes that are the same, and in today's technology, they're typically activated carbon. You might see some companies talking about carbon nanotubes or graphene, things like that, but the vast majority of production today is activated carbon. The charging and discharging process is electrostatic, just moving ions to and from the surface of the electrodes. The reason that they're a capacitor is that when they're charged up, you can see the charges align along the electrodes, and that creates two capacitors, one at each electrode. So in essence, there's two capacitors in series. Because there's no chemical reactions, we can charge and discharge at almost an unlimited number of times. They can also be charged and discharged at very high C rates. If you're normally working with batteries, that's a key parameter for a battery that can affect lifetime. With supercapacitors, we're not really concerned about C rates. But since the energy storage is only electrostatic, it occurs along only the surfaces of the electrode, it's going to be lower energy density. And so the ratio of the energy to the power means that discharges are typically in the range of 1 second to 1 minute. They can do much longer times. It becomes an economic case on how large and costly it gets. So these are typical times that we're discharging. And you'll see some examples maybe where it's a little bit longer than that as we look at some of the other features of the products. One design note shown here in the bottom left graph is that the voltage does drop like any capacitor as it's discharged. So the green line is the voltage and the blue line is an example of a constant current discharge. And so to optimize the use of energy, we want to use as wide of a voltage range as possible for your device. Looking at lithium-ion batteries, and I'll profess I am not an expert in lithium-ion batteries, but obviously they're one of the more popular energy storage products, if not the most popular these days across a large variety of applications. They work through an electrochemical process. The electrodes are different materials, one being carbon, the other one typically being a metal oxide. And in this case, you still have ions being released and moving, but the primary charge discharge mechanism is through the electrons correspondingly move. Okay, as side reactions occur to limit the desired reaction, chemical processes are also very temperature dependent. So the number of charge discharge cycles is limited in number and in temperature range. However, with charge stored chemically, batteries, as we all know, are very high energy density, but again, relatively lower power due to the reaction rates. So this leads to discharge times typically being in the 5 minutes to hours kind of range, a few hours. The upside as a designer, if we look at the discharge curve, is that the voltage variation is more or less flat, especially compared to a supercapacitor.
Hey, Jason, I'm sorry, your screen is not advancing, so we're still seeing the Supercap slide.
Okay, sorry about that. Here we go.
Thank you.
Yep, sorry about that. Okay. Yeah, so in the bottom left here, you can see the discharge curve. So here the voltage is fairly flat until you get to much higher depth of discharge, and then it will start to drop off. But this makes it a little bit easier for design in of some systems. Okay, the last technology that I'll talk about are lithium capacitors, also known as hybrid capacitors. They're a combination really of the lithium-ion batteries and the supercapacitors. Like a battery, they have asymmetric electrodes, meaning they're not the same materials. In this case, one is activated carbon, the same as a supercapacitor, and the other is a graphite doped with lithium. So the movement of lithium in this case is much more limited than what you see with batteries. And the primary charge discharge mechanism is the negative ions moving in and out of the cathode. So we're trying to stay in the operating range so it looks like a capacitor as you discharge. And indeed, that's what you see in the discharge curve as the voltage drops under a constant current discharge. So what do we get from that? It's really a device that is somewhat in the middle. We get higher energy, not quite to a battery, but more in that direction, but also higher power than a battery from the supercapacitor construction side. Most importantly, you get a very high number of charge discharge cycles. So typically a battery is going to be in the hundreds to thousands of charge discharge cycles. The pure supercapacitor is going to be hundreds of thousands to millions. The hybrid capacitors are going to be in the hundreds of thousands of charge-discharge cycles. So as you can see from the construction and the description, that the energy is going to be much greater, about 10 times than a supercapacitor, but still about 1/10 of a battery. And again, the power significantly higher than a battery, but not quite as good as a supercapacitor. With that combination, they fill a hole in applications where you need a few minutes of discharge time. So if what I described before, where supercapacitors are up to a minute, batteries are in that 5-minute and to hours range, a hybrid supercapacitor is going to fill in that gap from 1 to 5 minutes of discharge time. And again, these are kind of general rules of thumb. There are instances where we see the different technologies crossing over into different discharge times. If we look just at kind of more side-by-side comparisons of the two different types of supercapacitors, here in the left-hand column, a traditional supercapacitor or EDLC, where the electrodes are the same, and then the hybrid supercapacitor. Again, the traditional supercapacitors have higher power. They're going to last longer. Whether we look at charge-discharge cycles, so you can see here 500,000 to 1 million plus. And we've certainly seen test data where they're over $2.5 million charge-discharge cycles. Traditional supercapacitors also work over a broader temperature range from -40 degrees to +85 degrees C. So your full industrial temperature range is pretty typical with them. So I mentioned earlier, hybrid supercapacitors have about 10 times the energy of a traditional supercap, while still having a very good cycle life at 500,000 charge-discharge cycles. One key is also that they work at higher voltages. So that battery side of the construction basically makes it look like there's a battery in series with the supercapacitor. And so they typically operate up to 3.8 to 4 volts, depending on little details in the chemistry. Traditional supercapacitors today operate up to 3 volts. So for some systems, you can easily put them in series if you need to get to higher voltages. From a safety standpoint, both technologies are very safe. There's no thermal runaway. But the traditional supercapacitors, they can be short-circuited or discharged to 0 volts that a lot of customers like for safety reasons, particularly for maintenance reasons. Comparing batteries and hybrid supercapacitors, the defining features are in energy versus charge and discharge cycling. So we'll look at some of these things as we get into the applications. But again, lithium-ion batteries, typically they're 5 minutes and longer, although we have seen a few where they run down to 3 minutes. And we do see customers that implement them for shorter discharges, but they're typically having to oversize it because of the power levels. They have very low self-discharge, so the modern lithium-ion batteries you can let sit on the shelf for a long time, and you don't see a lot of voltage drop over time. And the cost per watt hour. So because of the energy density, the cost per watt hour is going to be significantly lower. And this typically manifests itself in a lower upfront cost. But then because of replacements, it's going to be more expensive over the lifetime. Both technologies do have low self-discharge. So the hybrid supercapacitor, as I showed on the previous slide, is going to have much lower, about 1/10 the self-discharge of a traditional supercapacitor. So that's why we put it on the comparison slide here, much closer to batteries. A long lifetime, typically 10 years and longer, especially at room temperatures, and the long cycle life. So if you're doing a lot of charge discharges, you can use the hybrid supercapacitors, put them into your design, and not have to worry about replacing them over the lifetime of your device. Again, from a safety standpoint, no thermal runaway. Even short-circuiting them, it will shorten the lifetime, but does not create a safety hazard. So here's a comparison of some actual products on the market between the different types of energy storage. So the first column is a traditional supercapacitor, very common 25 farad 3-volt part, takes up about 5.3 cc's of volume. The HS is the same size part, but in this case, you can see it holds 220 farads at 3.8 volts. And then two different types of batteries, a lithium ion, which I have discussed, and then nickel metal hydride. So again, another common rechargeable battery. So what we see is on the energy density side, it goes up as you go from left to right. The batteries maybe being in the same range, at least on the right-hand side there. But the energy density, again, much higher with the batteries and the hybrid supercapacitor being in the middle. I will say that the battery capacity is definitely very dependent upon the load or the current that you're drawing from it and temperature, much more so than either of the supercapacitor technologies. On the other hand, you can see the differences in peak power with the traditional supercapacitor being the highest, and again, about 10 times what you see from a lithium ion battery. And the next line is the cycle life, which I talked about, again, getting into orders of magnitude higher with the supercapacitor technologies. So what's this lead to? A common parameter that we look at is how much energy can you transfer over the lifetime of the product? And again, because of that cycle life, the supercapacitor technologies are much higher in terms of energy transfer over lifetime. And then the other key from a design standpoint is what temperature range do you need? Again, the supercapacitor technology is working down to lower temperatures, traditional at -40, the hybrids -25 to -15, depending on the exact product you pick, but also working up to the higher range up to 85 degrees C with voltage derating. Okay, you can see the batteries much more limited down to freezing temperature, and some of them do work down to below freezing, but with much more limited current. Okay. And so the key is, finding the right technology for different applications. So one design aspect that we see quite common in the industry is how do we optimize your power system for different applications? And so we do see quite a bit of using batteries and supercapacitors in the same system. And so here's 3 examples of how they're utilized. Obviously, also we have several systems where one or the other is used, but this is looking at combinations of the 2. So the first is a very simple parallel combination of a supercapacitor and a battery. This is the most common of what we see in IoT applications. Very low cost, so not a lot of extra parts here you can see, simple. But the supercapacitor is not optimized because it's fixed to the battery voltage. So in essence, you get basically a voltage divider, and the Supercap can reduce the current on the battery, which is one of the main lifetime limiters for the battery. And this is what we see most commonly in IoT. And it reduces the overall resistance of the energy storage, and so therefore you can get to higher power as well. And then we also see customers, they'll separate different loads in your system. So if you have something that draws a kind of constant current on all the time, they'll use the battery to power that. And then for either critical loads for backup application or pulse loads like your communications radios, they'll use just the Supercap for those. So again, there's not a lot of extra components here. It's low cost, fairly simple system, but it depends on what loads you have in the system and can they be optimized for each technology. And then finally, what we call a smart system. It optimizes the use of the battery and the supercapacitor. You have a DC to DC converter in the middle with independent inputs. And so they can optimize the output of the Supercap and the battery You can limit the current on the battery, for example, and then use the supercapacitor for the current above that level. This would maximize the lifetime and the runtime. So with limiting the battery current, you'll have more energy stored, and so that'll allow your load to run for a longer time, but also extend the life of the battery. So we see this most commonly in transportation power units, so IoT going into vehicles both on-road and off-road. This is an example of a case we took, just an example where there's a 6-watt constant or average power on the system for 40 seconds, and then there's a 40-watt pulse for 10 seconds. And this is where we see types of load profiles where supercapacitors can bring a lot of value. So we're going to limit this, in this case, the battery current. And so originally it was just 3 battery cells in parallel, and it could support the system, the full current of the system, for about half an hour. So we added a supercapacitor. In this case, it's a traditional supercapacitor EDLC that's a 10 farad part. And the concept is that the supercapacitor is going to relieve the battery of those 40-watt pulses. And what we saw is that the system runtime, because we're limiting the battery current, got out to just over 2 hours. And then also with that lower current on the battery, we expect that the overall lifetime is going to be extended as well. Okay, so that's a fairly cost-effective method to extend your runtime if you have very pulsy type loads and running them on a constant basis. So we'll talk about some application examples here. If we look overall at wireless IoT and what different standards are used, and the reason we look at what the communication protocols are is that in a lot of cases is the key factor for using supercapacitors, whether it's a hybrid supercap or a more traditional one. Right, so I'm sure all of you are using various ones of these in your designs, whether it's Bluetooth, Wi-Fi, LoRa, or NB, with over GSM or GPRS for long range. I won't go into the details here. What I did want to point out is typical what we see from customers as far as voltages and typical currents when they're transmitting. You can see in the second column there. And as those pulses get higher and really are pulses operating, then it leads more to supercaps being used. And so, for example, in the first line with Bluetooth, that's typically always running, right? And you might get up to 10 milliamps, but typically you're pretty continuous at 2 to 3 milliamps. And so we just classify those are going to be typically just battery power sources. So whether it's lithium ion or nickel metal hydride. Okay, so we see this in a lot of, or even a primary battery, I should mention. But in applications, right, we see this in a lot of indoor consumer products, audio, and smart home appliances. Now, as we start getting into more industrial applications, Wi-Fi, right, where you're going to have 200 to 300 milliamp transmission and maybe up to 100 milliamp read. So at 3.6 volts, so you're going to get much more pulses. The time aspect can vary depending on how much data you're transmitting. So in this case, we still see batteries in these applications, and we really see them in all the applications on the page because you want a long runtime. But they're using supercapacitors to extend the battery life and also the temperature range. And so we see this in security systems, smart city applications, and different types of sensors. So we get to longer range type communication protocols like LoRa. Again, very low current on a continuous basis. You can see they're typically in the 50 microamp range, but then they have 40 milliamp pulses. So again, for the 50 microamp continuous, customers are typically using a battery. Obviously, if you have another source of energy supply, it could be just a supercapacitor, but in this case, customers that we've worked with will parallel a supercap to extend the transmission range or the operating temperature. Right? So these are typically going to be outdoor type security systems, other types of smart city applications, EV chargers, which I'll show a more specific example of, and industrial sensors. And then lastly, on the NB IoT standard, again, you can see much higher currents in a pulse depending on how far you're trying to transmit, but then very low power sleep modes. So in a lot of these cases, we're seeing a primary lithium cell called a lithium thionyl battery. So that's designed to last whatever the life of the device is, and we see up to 10 to 15 years is typical. And then at either a standard supercap or a hybrid supercap, and maybe a secondary battery as well. And so these are used in asset tracking, smart metering, and we'll talk about some of these applications on the next slides. So a lot of text here on the slide. Basically, think of this as backup power and pulse power for status reporting. In this case, the design that we did is with an EV charger, so it can report status to utilities and applications that are pulling data from and status, and provide backup if it's disconnected. So for some reason, if it gets disconnected, it can alert somebody that that's happened. Other similar examples, industrial machinery. We see a lot of DIN-mounted devices or embedded devices that are also transmitting data. Remote type devices like ATMs, vending machines. We've done quite a few gambling machines for casinos, and then billboards and displays as well. So we're providing, the supercapacitors are providing safe shutdown and then power outage reporting. So the safe shutdown might run a little bit longer, into tens of seconds or even minutes. Here we gave a 100-watt example for 2 seconds, but I've seen several minutes or a few minutes for a safe shutdown. Power outage reporting. So again, this is a data transmission typically in the less than 30-second range. So there's different solutions for powering these. In a lot of cases, it's at the home. So we've seen lead acid batteries used, a 12-volt, pretty small lead acid battery, 12-volt, 2 amp hour. You can see, but also fairly large there. And with lead acid batteries, typically issues with, is it actually working when you need it? So particularly for the backup applications, not the best technology to use for important data transmissions. The second solution we offered is with a hybrid supercapacitor. In this case, took 8 220 farad hybrid supercapacitors, and this depends on what the data transmission cycle is, or the safe shutdown, how much power you need and for how long. So you can see the temperature range that was required from the customer. Again, there's no flammability or outgassing issues that you might see with a lead acid battery. They're mounted directly to the PC board, so they can go with the rest of your electronics, easy to assemble, with a long lifetime, and then all the safety and environmental certifications. And lastly, a traditional supercapacitor, you can see here it takes a lot more volume to meet the same energy as the hybrid capacitor, but again, extends the temperature range and fewer disposal issues. There's no lithium inside the cell. So from a safety standpoint, a lot of times this is preferred with customers. The second application I'll talk about is asset tracking. So this manifests itself in a lot of different ways, but the main one we see is on vehicles, whether that's containers, train cars, truckloads, agricultural vehicles, construction vehicles, motorboats. And in a lot of cases, they're powered by a small solar panel that's mounted onto those vehicles. And typically there's a GPS operating and then communicating over a GSM network. So the solar obviously collects during sunlight, and then either battery or supercapacitor that it charges and then can use that during nighttime. So the power during transmission, typically we're seeing for a GSM signal, something up to 3 amps for about 20 seconds. But then again, you see the rest of the system is very low power. So when it's not transmitting, it only pulls 1 milliamp. And the customers typically want to be able to run for about 24 hours without needing to recharge. So if it's a full cloudy day and they're not able to recharge, the system can still run. So the issues with the battery particularly is temperature range. So a lot of these are mounted in locations where sunlight will hit the unit that's being mounted. So it's not hitting the batteries or supercapacitors directly, but that whole package. So you get a lot of solar heating. To charge lithium ion off of a solar panel, it takes a fair amount of electronics to keep the lithium ion safe. And then fire hazards are a common thing that we hear, especially from vehicles, and any hazardous materials are frowned upon. So, and then a common area also with batteries is it needs to be replaceable because of the lifetime. And we also see that sometimes they're stolen and taken, so they'll want to take them out of the system. But they are still used. Obviously, detailed a lot of the issues with batteries, but they can provide a lot of transmissions per day, and they last about 3 to 4 years in this application. So again, we looked at hybrid supercapacitors and the standard supercapacitors. The hybrids can also provide a very small package. You can see actually smaller in this case than the lithium ion, which had to be oversized. It does depend a little bit on how long the transmission cycle is. But again, you can mount them directly to the PC board and typically over 10 years lifetime. And then traditional supercapacitors, a little bit larger than the hybrids, but give some advantages. Here, one design aspect, because of the voltage drop as it discharges, we're showing having a DC to DC converter in the system. So that does obviously add some complication to the overall system, but optimizes the use of the supercapacitors. For that, you get obviously a much wider temperature range, no flammability concerns, again, a very long lifetime. And because of that, we can design it to the lifetime of the vehicle or whatever it's being, the device is being mounted to, and it can be hidden, and therefore you get rid of the issues with things being stolen and being lost. Our most common application that we put into the IoT space is smart metering. So these are obviously your digital meters. And in this case, I'll talk about water meters because there's always a battery running the water meter, and they're expecting about a 15-year lifetime out of this battery. So it's a primary battery, the lithium thionyl battery. And so power for the transmission, again, you can see it's not a huge amount of current, 40 milliamps for about 5 seconds. And they're typically transmitting once a day. It might be a handful of times if there's something else going on in the system, but not a lot of transmissions. But when they only have a battery in the system, even just one transmission a day over those 15 years is going to take about 20% of the battery capacity. So again, they would have to oversize the battery to take on all those pulses. And then it just exacerbates the problem if you're doing more than one transmission per day. So the solution is to combine the supercapacitors, traditional supercapacitors, with the lithium thionyl battery. In this case, to match the voltage, we'd have 2 supercapacitors. A 1 farad is typical. There are larger ones depending on how much current they have in that data transmission. So the supercaps provide the current for pulses and fast reaction. This battery in particular has trouble going from sort of a very low current state up to that higher current state very quickly. The downside and thing that we have to take into account is that the Supercaps do have about a 2 microamp self-discharge. So that's going to be constantly draining on the battery, and that takes about 10% of the total capacity. But you can see overall, you get a savings, an extra battery life of about 10% there. Plus, if you're doing more than 1 transmission a day, it's just going to multiply that. Smart metering with a GSM signal. This is typical in gas meters. So again, comparing, in this case, just with the lithium thionyl battery against the supercapacitors, peak power of about 1 amp for 20 seconds. And so we're doing just the peak current by what we're calling a secondary power unit. So the rest of the meter runs off of some other power. It could be wired or off the battery. So similar, because of the voltages, we're putting 2 traditional supercapacitors in series. Very good performance in cold temperatures and a longer lifetime. Again, we typically see a DC to DC converter in that case to optimize the use and over the range of the radio that's being powered. Okay. You can alternatively use a hybrid supercapacitor. In this case, because of the higher voltage, you just need 1 part. And the key here is it has significantly lower leakage current. So if it's working in conjunction with a battery or powering off the battery, it'll have significantly longer battery life in that case. So smart sensors we see in a lot of different industrial applications as well as agricultural. Typically where we're, again, charging off the solar panel that I described earlier, and then power for the data transmission is on the order of 100 milliamps for 20 seconds. In industrial spaces and a lot of the agricultural sensors are outdoors, so a wider temperature range. I would say typically probably even wider than what's shown on the slide here. In this case, a particular sensor we worked with was actually inserted in underground, so I think the temperature was a little stabilized by that. This was a moisture, basically a moisture sensor going into the ground, and they're communicating over LoRa. So again, maybe not go into all the details here, but combining the solar with a hybrid supercapacitor, very effective, and the higher energy storage of the supercapacitor allows us to run the system overnight. Now, the other solution was to use the lithium thionyl battery described earlier with a supercapacitor. So the lithium thionyl can have a lot of energy for the constant usage, and then use the supercapacitors again for the data transmission. Okay, the last application I'll talk about is in the transportation space for emergency backup. It's an e-call unit with a GSM connection. And so things like emergency power for EVs, for passives, but EV door latches or other similar types of applications. In the e-call, what's happening is if you get in a crash, the system will automatically make a call to emergency services and give status of the vehicle, what sensors have been triggered, if airbags have been set off, things like that. And that way, if the person's hurt and can't make a call out, it'll automatically go and get somebody there. So different solutions depending on what additional functions a customer might be trying to put into the system or a designer. So the first would be just to send an SMS solution. So it's short duration, less than 10 seconds. We can do it with a very small supercapacitor pack, lasts 15 years over the full operating temperature range. As you get to more sophisticated solutions, depending where the driver can have verbal communications, so they have a talk option. And now we get into higher energy requirements. So We could do it with hybrid supercapacitors that would be used because of the temperature range and the safety aspects, or a lithium iron phosphate battery, going to be much smaller, but does run into troubles with the temperature range and needing replacement over time. I'll briefly go over our products from an Eaton Electronics division standpoint. Our division, we have 3 different product lines: magnetics, supercapacitors, and circuit protection. So you can see all different types of magnetics for the IoT space, for the power conversion, noise filtering, and RF circuits. One aspect I didn't talk about on the supercapacitors is we do have products specifically for real-time clock backup. So this is one application where the supercapacitors are going to be providing backup power for probably a week to 2 weeks kind of time frame for that low power state of the real-time clock. And then circuit protection, whether that's over current, over voltage, and particularly for for IoT applications, we see a lot of ESD protection devices in those designs, and then battery short circuit protection. On the supercapacitor side, we do have the broadest product line in the industry. So we go from coin cells up to large systems. So you might see those systems as grid energy storage, large megawatt size backup power for industrial uses. But for IoT, the scope of our products goes from the coin cells I just mentioned up to the hybrid cells. And in this space, typically the largest that we see is an 18 millimeter size diameter can by 60 millimeters at 100 farads. But a lot of devices in that small size of 1 farad or half a farad. Yes, I am saying farads, not microfarads or picofarads. For energy storage, it's typically in the farads range. Just to show our history briefly, we've been in it since the late 90s. Eaton, there was a couple of acquisitions in that time frame, but since 2012, it's all been under the Eaton umbrella. And you can see the products released along the top, kind of core technologies and adding different form factors. And then along the bottom, there kind of larger modules, which wouldn't necessarily apply to IoT. And one of the key factors for supercapacitors and the growth is getting more higher energy density, which has been by developing not only larger sizes that can have more capacitance, but from a pure technology standpoint, increasing the voltage. So typically all of the factors, whether it's energy or power, increase as the rated voltage squared. So a 10% increase is going to give you in voltage is going to give a 20% increase in power and energy. Okay. Thank you for your time today. I hope you found it informative. And if there's any questions.
Thanks so much, Jason. Wonderful presentation. We did have one question that came through during your presentation. And again, if anyone has any additional questions, feel free to put those in the chat box, or you can unmute yourself at this point. But a question here from Chris Waters. Does using SC in your IoT device afford you some kind of green energy claim for marketing purposes along the lines of Energy Star?
Yeah, good question. So I would say it can. There's probably other aspects, in the design that would directly relate to Energy Star, but we do know some customers that have made that claim when they implemented supercapacitors. I think one of the bigger claims that customers have made, perhaps not as much on the Energy Star side, but on the green energy, is that there's no heavy metals, no thermal runaway. So from a safety and environmental standpoint, they're much safer. The traditional supercapacitors are really made from aluminum, a high-tech paper, and the carbon that I mentioned. So green materials that are much easier to recycle. We still don't recommend throwing them in the garbage, but they can be handled by any industrial electronics recycler.
Thanks, Jason. That was exactly my question. Yeah.
Okay.
Is there something for green? Is there a name for it? I mean,
so we, sorry to get a little bit legal in discussions with our lawyers. They always caution against just making a blanket green energy claim, but so that's why we say it supports that, and environmentally friendly materials is kind of the way that we state it. And then, you know, if you look at the certifications, so they're halogen free, they meet all the RoHS standards from around the world, and then REACH in Europe. So those are typically the ones that you would see.
Thanks, Jason. And thanks for the question,
yeah.
Chris.
a pleasure.
Another question came in here, Jason. What is the total cost of ownership comparison between battery and Supercap technologies?
Yeah, of course, that's pretty specific, but we've done a lot of TCO studies where the Supercaps are, you know, half the total cost or a third the total cost of batteries. It does get pretty specific into the exact situation, but we've seen it as high as that.
Awesome. Thanks, Jason. Leave it open for just another minute for questions. While we're waiting, Jason, what's the best way if someone has additional questions or would like to get in touch with you? Do you prefer LinkedIn, or we can drop your email in the chat box?
Yeah, you can certainly put my email in the chat box is fine. Yeah. Or LinkedIn if people are more comfortable with that. I'm also on LinkedIn.
Great. Yes, that is correct. Someone asked if this was being recorded. Yes, this was recorded. It'll be posted right its YouTube channel and then posted to the meetup page where you registered for this event. And I'm just trying to find your email, Jason. I'll pop it in. Awesome. I'm popping it into the chat box now for those who would like to reach out to Jason. I think that's all the questions, Jason. Really appreciate your time. Thanks for being with us today. And thanks again to AEM Group, specifically Penny Hoagland, for being with us. A question actually just did come in. Any issues for transportation for Supercaps?
No, there are no transportation. So they have their own categorization under the shipping regulations. And there are currently no limitations on that. For the, I mean, no limitations. You do need to be mindful to ship them uncharged in the case of the traditional supercapacitors. And then there's a general, make sure they can't be short-circuited during shipping. So pretty light regulations on them, but you don't have to declare them as hazardous goods or dangerous goods.
Thanks so much, Jason. All right, everyone. That's all the questions I'm seeing. Thanks again, Jason. Thanks, Penny at AEM Group. Thank you all for being here. We'll see you at the next Lunch and Learn. Take care, everyone.
Thank you.
Thank you.